Now it's starting, right? So this is day 20 of fluids and plasmas, and now we're getting to plasmas. So I've said everything that I feel like saying this year about turbulence. That's not entirely true. I'll probably say a lot more when we go over the homework. So there's a homework up on turbulence. Oh, I need to have office hours for that. When did I make it due? Next Thursday? I'll have office hours next Tuesday and Thursday, I think, because I don't think I made it due on Tuesday. It's Thursday today, right?
Yes.
I don't have internet on this thing down here, so anyway, probably homework, or probably, so I think there's a reading due Tuesday, because I wanted to say all this stuff before I gave you the reading, and then there's a homework due on Thursday. Today, we're going to talk about plasma physics briefly, and then we'll get to the MHD limit, which is a limit of plasma physics. So, yeah.
The reading is due on Monday at midnight, but the homework isn't up.
The homework isn't up. Okay.
The homework's not posted.
Okay, cool, sweet. That means I forgot to post it. That's why I couldn't remember when I posted it for, because I hadn't done it.
Mm-hmm.
Cheap brain. Anyway, so that'll go up tonight. It's written. It's finished. I just need to post it. It's about turbulence, so we can all feel the wonders of being confused about turbulence. Today we're going to get into magnetohydrodynamics, and this is not a word I write out all the way very often because it's so long and obnoxious, so we just call it MHD. This is what I spend most of my time doing. I got hired because I know MHD. So MHD is the limit of fluid dynamics with magnetic fields where you can ignore the electric field. So I'm going to spend a day showing you in what scenarios you can ignore the electric field, and I'll show you the full set of MHD equations. So basically we take Navier-Stokes, we add the Lorentz force, and then we have another equation, that's the induction equation, that gives us how the magnetic field evolves. So like half of you are in E&M right now, is that right? So the Maxwell's equations stuff will be familiar, but nothing else. There's going to be very little overlap between E&M and what we do here, because what we do is all MHD. Take did some MHD when he taught E&M, so I don't know. Is Toby doing it right now? Who's teaching E&M right now? Okay, I don't know if he does any MHD. He might.
I don't think he does.
He did not.
But
He
didn't. Okay.
He didn't do it this.
That's okay. So we'll do it here. So this is what I'm going to talk about. I'm going to talk about Maxwell's equations, and then I'm going to complain about units. So you are doing it in SI. I am an astronomer, and we use CGS for reasons that I will explain. It's only little differences. The bulk of the equations are the same. It's just where the epsilon knots go. And then I'll talk about photons, and I'll show you where light comes from. Then we'll talk a little bit about charged fluids. Then I'm going to talk about, this is what I'm going to spend the bulk of the lecture on, are these 4 length and time scales. So the basic idea, I'll cut to the chase right now, electrons don't weigh anything, right? Electrons basically massless, I mean, more or less. When you're comparing it to an HCO plus, it's way, way smaller. When you're comparing it to a proton, it's way, way smaller. It's 1,000th of the proton size, right? So the electron has very little mass. So when you have a little bit of electric field, they just race right along and get rid of it. So they will move to cancel out the electric field basically instantaneously. Not instantaneously. We'll talk about how long it takes. So we'll talk about the response time scale. Okay. Let's go back here. I'll just write down Maxwell's equations. If I were mean, I would make one of you come up here and write them down, but I'm not going to do that. Okay, so what's that?
We use Gaussian units in E&M, so I don't know where the constants would go.
Oh, you use Gaussian units?
Yeah.
You're not using SI?
Well, yeah, the way Picaros does it, he uses Gaussian because he follows Jackson. The graduate textbook.
He uses the red one though, not the blue one, because the blue one's in the SI.
Yeah, the one that has Gaussian units.
Oh, really?
Yeah.
Okay. Anyway, well, okay. Then you're more on my side anyway. So in SI, which is what a lot of people use, this is what Griffiths is in. It's what the blue Jackson is in. It's what a lot of people use. It's what all the engineering uses. It's what you use in 2048 probably. So the epsilon knots all go away, so you don't ever have to worry about it. There's no extra factors. There's just a 4 pi. So okay, in SI, the first one that we talk about is div B equals 0. Actually, let's take a step back for a second. What are Maxwell's equations about? Maxwell's equations are about writing div A and curl A. Helmholtz's theorem, I think it's Helmholtz, one of those old guys who did a lot of calculus, has a theorem that says that if I know the divergence of a vector field and the curl of a vector field, that uniquely determines the vector field up to a constant. Constant goes away when you differentiate, but I can't add anything. There's no other gauge freedom when we have both of these. So I have some gauge freedom. What do I mean by gauge freedom? So if I have the curl of a vector field A equals some other vector field B, I can add A plus div or plus grad phi. This is still true because the curl of a gradient is 0. It's not true for this one though, because then that gives me a del squared of that phi. So when you write down your vector equations, there's a little bit of gauge freedom, but it's only up to a constant. There's other gauge freedoms when you get to E and M where you can add stuff and it doesn't change the equations that we'll talk about. But when you supply both, then that basically fixes the two fields. So Maxwell's equations are 4 equations, 2 for B and 2 for E. They're the div of B and the curl of B, the div of E and the curl of E. So these 4 equations completely specify the vector field. Now, div B has caused me more emotional trauma than any other equation. Full stop. Because
No magnetic monopoles.
yeah, so because when you try to do it with code, it's really a headache to keep div B equal to 0, and when it's not, things blow up. So I spent many years of my life trying to numerically keep div B 0 in complicated equations. It's the simplest of the equations. It's the one that doesn't change. It's also kind of redundant because, as I'll show you in a second, we have an equation for what the curl of E is, and we know that this is going to be 0. But anyway, regardless, div B is 0. Let's do div E. Div E is 1 over epsilon naught rho free. So this just says that charges end on electric fields end on charges. That's what this equation says. So if I have a charge, I can draw a little surface around it and find out what the electric field is. So charges make electric fields. Now, okay, there could be a universe where there exist some magnetic monopoles. That's a fascinating thing to think about, but I'll show you why there could be magnetic monopoles in a second. They're right here. Curl of E is minus dB dt. This is the one I have to look at because it doesn't have a C on it. The other one has a C. And then curl of B is mu naught J plus epsilon naught dE dt. So this is how Maxwell's equations look. Oh man, my board styling is terrible. I should have written it, given myself more space. These are Maxwell's equations in SI. In CGS, specifically Gaussian units, div B equals 0, div E equals 4 pi rho free, no dumb constant to measure, just 4 pi. Curl E is 1 over C minus dB dt. This C is important. What's this C doing? It's making sure that E and B have the same units. So this is a length per time, here's a time, and here's a length, and they all cancel each other out. So E has the same units as B. Yeah.
Why do you need that when going from SI units to CGS? But you don't.
This C?
Yeah.
But I don't need one here?
Yeah.
Because E is different. So SI describes an electric field and a magnetic field that are a little bit different than what you describe in Gaussian, the Gaussian units. One of the big differences is the units and the equations are different. The units on the electric field here are different from the units here by velocity. Does that make sense? I mean, can you see that? So this is, these are units, we'll call them Q. This is Q per length, and this is whatever, W per time. So the ratio of the electric units and the magnetic units are a length per time, so they're a velocity. But when you take relativity, you'll learn that I can fold magnetic fields into electric fields, which is why probably Jorge uses Gaussian units. I can fold electric fields and magnetic fields into each other. If I'm going fast enough, electric fields turn into magnetic fields. I'm not going to get into any of that right now. But because of that, we like this symmetry in E and D having the same units, and then the C takes care of the units. It's also actually an important constant. C lives here because it's the appropriate velocity to be here. And I'll show you why in a second. And then the last one, curl B is 1 over C, 4 pi J, sometimes there's not a 4 pi there, plus dE dt. And I apologize for my bad board skills. So the main difference between, and then I was going to write down the force law. Okay, so here's one of the big reasons. The force between two charges, 1 over 4 pi epsilon naught, Q1, Q2 over R squared. So now I've got this epsilon naught that I A, have to remember, and B, have to measure. I have to know what this epsilon naught is. In Gaussian units, F equals just Q1, Q2 over R squared. So in this equation, I have picked a unit for charge. And epsilon naught has to make that unit make sense. In CGS, the unit on the charge just comes out of this. So the unit on the charge is what? It's the square root of a force times a distance, which is weird. I don't like units with square roots in them, but we get them. It's the thing that happens. So here a charge is a square root of a dyne times a centimeter, and here a charge is whatever. There's an epsilon naught in here, so I can call this really whatever I want. These units are arbitrary. Another important difference is the force between two parallel wires. So this is the force between two charges. The force between two parallel wires is equal to mu naught over 4 pi times I1, I2 over D, whereas in CGF, DF, DL is just I1, I2 over D. There's a 4 pi's in there. There's a C squared. This is not an equation I write down very often. So when I go to define what an ampere is, so when we're defining the units, in SI you have to define an ampere. So there's another unit that you have to define called the ampere, and another constant that you have to measure, mu naught. Mu naught and epsilon naught, I'll show you in a second. Mu naught times epsilon naught is 1 over c squared. All the way at 1 over c squared. So epsilon naught is not a free constant, but mu naught is. Whereas in CGS, the only constant to measure is c squared, and we've measured that really, really good. And there's no other constants to measure, it just determines the unit. So it's a more natural set of units to use. But that's what we'll be using. Not as much of an issue since you're already using Gaussian units. So Maxwell's equations, we'll come back to, I should actually leave them up. I'm going to leave those guys up. I read this. Here, I'm going to draw a box around this so that I don't erase it, because I need those. Okay, so when can I get rid of... oh, no, sorry, the next thing I was going to do. So, okay, we're going to take this and this. So, del cross E equals, let's do it in SI because we feel more clever and magical in SI. I'll show you in a second. So curl E is minus dB dt. And curl B, let's say there's no free current, is just mu naught epsilon naught dE dt. I want a wave equation. So I'll take the curl of this one and the time derivative of this one. Hey, we've done this before, right? I take the curl of one and the time derivative of the other, and I get a wave equation. That's how we got sound waves in the first place, yeah.
So if you take the curl of del, it becomes Laplacian in the same way that taking the divergence of del becomes Laplacian?
No. Curl of grad phi is 0. That's always true. Curl of A is more complicated. It is grad of div A minus del squared A. Now I should have used B here because that's what I've got. I've got curl of B. This is just going to turn into a minus div squared. Yeah, that's a minus. So I'm left with just, this turns into a div squared, and this turns into a curl of dE dt. Up here, I'm going to again get a curl of dE dt and a second derivative of B. And I'm left with an equation. I'll add them all up, and I'm left with d squared by dt of B minus 1 over mu naught epsilon naught of dB dx squared equals 0. This is a wave equation. I boosted to one dimension in here somewhere, like right here. Does everybody follow that? Yeah.
So is there any reason why you write the dt squared b different than that one?
I was lazier at this moment than I was over here.
Okay.
Nothing really. Okay. Sloppy board stylings.
Could you not also write the 1 over mu naught epsilon naught as just c?
Well,
squared?
this is the magic. So they did this, Maxwell knew this. Maxwell had them written down with these mu naughts and epsilon naughts because the mu naughts and epsilon naughts were like, okay, what they were doing like really ridiculous things. Like they would take a stack of stuff and they alternate copper, lead, copper, lead, copper, lead, copper, lead, copper, lead, and that makes a battery, or maybe it's zinc, copper. I can't remember. I'm not a chemist. They make a battery and then they have this thing and they touch it to frogs' legs and the frogs' legs twitch around. That was the extent of their experimenting. So they were like, there was a lot of just horsing around in the 1800s. With these electric and magnetic fields. And Maxwell and others determined that this is a wave and it travels with a speed. They could then determine the speed here and find out that, well, they knew that mu naught epsilon naught when you did this was close to c. So they measure mu naught and epsilon naught and the product is close to c squared. So then this thing looks like a thing that travels at the speed of light. And then we slowly understand that this is a photon. This is where photons come from. So how does a photon travel? And why is relativity such a pain in the ass? Because of this. So at the end of the day, what sets this speed? So I'm going to rewrite this as, if we just used SI, the magic of, oh, we're so clever, goes away. But this just becomes c squared. And it's more obviously this is a wave that travels at c. When we did waves with hydrodynamics, there is a medium that the wave is traveling in, right? There's not a medium that this is traveling in. B is making E, and E is making B. This is like, do you ever watch those cartoons where Bugs Bunny's on a train and the track runs out and he's pulling track out of his back and laying the track down in front of the train like as it's going? I don't remember if it was Bugs Bunny or Daffy Duck, one of those old cartoon nerds. It's like that. You get a little bit of E, then you can get some B. You get a little bit of E, you can get some B. Now, when I have a fluid, if I'm moving with respect to that fluid, then I have to do a Lorentz boost. And my fluid has to be moving in the opposite direction. But there's nothing with respect to anything that I can be moving. I can't Lorentz boost any of these objects because it's already traveling at the speed of light. So what does that mean? That means that this is true regardless of how fast I'm going. Now, this isn't true. If I write down a wave equation in water, it's not true that I get the same speed no matter how fast I'm going because I can Lorentz boost and move with where the medium is moving at minus v that way and I'm moving at v this way, the wave holds still. I can do that. I can't do that here because there's no medium. There's no velocity. I have a velocity in the other equations. When I did this with sound waves, one of the terms was velocity, and you can shift the velocity. I don't have a velocity that I can shift here. So that means that everybody, no matter how fast you're going, is going to have to measure the same thing. That means that whatever reference frame you're in, you always measure the same speed of light. And that is why relativity gets so weird, because your measurement apparatus has to get longer to make that true. And nature is an asshole, and that's how it does it. Instead of making the speed make sense, it makes things get stretched, and it makes time slow down. So that's kind of cool. I'm going to stop talking about that because we don't do anything else relativistic in this class. But so there's some beauty. So whenever somebody asks you why you can't go as fast at the speed of light, this is why. You can just bust out this derivation. Now, it takes some practice if you just happen to get asked that at a party to do that without sounding like an idiot, to make that sound graceful. But that's all it is. Like, all of relativity is contained right there, or the reasons for it anyway. Okay. So photons. Photons are great. We'll do that big page of math second. We'll do this littler page of math. So here's the list of stuff that I'm going to do. So ostensibly, I'm an astronomer, and so what I like to do is astrophysics. But the MHD limit applies to all kinds of physical phenomena, and I'll show you when you can tell if MHD applies or not. So let's talk about these scales. So the first thing we're going to talk about is called the Debye length. So what kind of systems are we talking about? So let's say we've got a fully ionized plasma. What is a plasma? Anybody?
Hot gas.
Was that?
Hot gas.
Hot gas. Why is it? What makes it a plasma?
It's ionized.
Yeah.
I was gonna say, is it a fluid that we're like that's so hot that all the electrons kind of separate from
Yeah.
the nuclei?
Yeah, that's right. So you get it hot enough and the electrons come off. So you start with a solid, you get it hot enough, the bonds break and you get a liquid. You get it hotter, the bonds break and you get a gas. You get it hotter, the bonds break and you get a plasma. All the electrons come off the... Now it turns out all of the electrons come off the protons. And it turns out for a lot of plasma physics effects, you only need like 1 part in a million of your electrons to be liberated. You don't have to be really very ionized. It doesn't have to be completely ionized. There's differences between partially ionized and fully ionized plasmas. We're going to totally ignore that and just assume that it's ionized enough for whatever enough happens to be. We can deal with that later. So I've got some, for now, let's deal with a cloud of positive and negative charges. So we've got ions, which are the positive things, and electrons, which are the negative things. Now the ions, we can just treat them as protons, in which case they have a mass that's 1,000 times larger than the electron. That's the best case scenario. Other scenarios are, this is something else, like HCN+. That's a much bigger molecule than just a... Was that?
Hydrogen cyanide?
Yeah. This stuff is all over the outer space. Outer space is full of this. Or ammonia. You can ionize ammonia. Or big dust grains. So there are big grains of dust that have many tens of thousands of carbon atoms. There are buckyballs that are spheres of carbon. 60 carbon atoms make a sphere. I saw the coolest talk on buckyballs 2 years ago, maybe. Anyway. So the ions are all way bigger than the electrons. The electrons basically have zero mass relative to the ions. So if I just have let's say I have a sea of electrons, and I put one proton in the center. What do the electrons do?
Gravitate towards the proton.
Yeah. It's not gravity, it's electrifate. Let's go with gravitate. It makes sense as a sentence. They all get, so the electrons all combine near that proton. So then, if I take a big enough area, I can't see the proton because I have these electrons that made a wall around it. This is called screening. How much is it screened? Okay, so I'm going to do a little math. Some of this math I'm not motivating very well. I'm going to try to motivate it as I go. It's not a derivation that I'm going to ask you guys to do. So if you don't follow, that's okay. Well, if you don't follow, holler and I'll talk about it. So we'll start with del squared phi E. This is now an electric potential. This is different from the electric field. How do I get the electric field from the electric potential? The electric field is just going to be the gradient of the potential minus grad phi E. I'm going to immediately drop that E because I'm too lazy to carry it around. So del squared phi of E is div E is rho free, is the free charges. So I'm going to have some density of ions. We'll call it Ni. And I have some density of electrons. We'll call it Ne. Now, in principle, if I integrate, my fluid should be on balance neutral. It doesn't have to be. So if I average Ni and Ne, I probably get the same number, but they're not the same number. They're not the same functions. Because this is a function of x and t. Because the electrons can move around. So this is the local density of electrons at any, and the local density of ions. So del squared phi is going to be 4 pi times Ni minus Ne times the electron charge. And there's a minus sign here because of this minus sign. So Ni minus Ne, that's the net charge at any point in space. Does that make sense? Can you see okay, or is this in the way?
I can just do this, it's cool.
I do that a little better. Is that better? All right. So the density of ions minus the density of electrons gives you the net charge at any point in space. So del squared of that is going to give us, this is the net charge. This is the electric field, del squared phi. I'm going to pause it, and I think there might be a better way to motivate this, but I didn't come up with it while I was sitting at the dentist office with my kid this morning when I was writing my notes. So there might be a better way to motivate this, but I'm just going to posit that I'm going to stick a proton here, and the charge will fall off like an exponential. So we're going to call this n naught e to the plus or minus e phi over kt. Okay, so delta E over kt, e to the delta E over kt, is the Boltzmann factor. This is a thing that will show up a lot. E to the energy over kt. This This describes the competition between whatever system you've got. This could be the electric energy, or it could be excited ion, hydrogen atoms. It could be all kinds of stuff. So this is any kind of energy versus thermal energy. So E times phi is going to be the energy that electron feels, and KT is going to be the thermal energy it feels. So it's reasonable to say that the electron density is going to go like that. So then I can say, okay, Ni minus Ne equals what? Oh, let's Taylor series this, actually. Let's Taylor series this so that we get N naught times 1 minus E, 1 plus or minus E phi over KT. Why? Because Taylor's awesome. Taylor makes things linear, and when it's linear, you can solve it. And that's awesome. So Ni minus Ne is just equal to what? The 1 cancels. These two things are different by a minus sign, and we're just left with 2 times N naught times E times phi over KT. All right, this is this thing in here, and this is phi. So I've got del squared phi equals, I've got 4 pi, I've got 2, an N naught, an E, and a KT, N naught E over KT times phi. Did I do that all right? 4 pi, 2, N naught E over KT. Oh, there's another E. So I've got the second derivative of a thing is equal to a thing. This is positive. Oh, maybe that's negative. Doesn't matter a ton. I can write this as phi is then equal to some phi naught e to the 4 pi n naught over kt phi x. So we can rewrite this as phi equals phi naught e to the minus x over lambda d, where lambda d equals, where am I at? Kt over 8 pi n0 e squared. Did I make it on the thing? Okay. All right, what did we do? Okay, so we said d grad phi squared is my charge. I made some stuff up about my charge to make it look like the potential again, and I get an exponential. And this is basically the length scale over which your charge is screened out. So your net potential is going to fall off like 1 over the Debye length. So if I'm looking at structures, if I've got some plasma, and I'm looking at things in that plasma that are bigger than the Debye length, I can't see the electrons. I can't see the ions. All I see is a neutral plasma. So the Debye length, lambda d equals kt over 8 pi n naught e squared. So if I'm looking at things that are bigger than the Debye length, then I can ignore the electric field, because the electric field makes the electrons move and cancel out the electric field. So that's what electrons do. If I put an electric field and I've got a bunch of free electrons, the free electrons will just move until they cancel out that electric field. And that's what the Debye length does. It tells us about how long that is. So that's just one thing. I can have a totally neutral plasma that's radiating in the X-ray and giving me cancer. That's bad if I'm cancer reverse, even though it's totally neutral. So we got to worry about time scales too. So let's talk about 2 different time scales. So the one length scale we care about is the Debye length. The time scales that we care about are called the cyclotron frequency. One is the cyclotron frequency, and the other is the plasma frequency. So the cyclotron frequency is free electrons around B fields. And the plasma frequency, there's a couple of different derivations of the plasma frequency. There's one that the book does that I think is a little more cumbersome than you need. You can do it with just the electric field that I'm going to do now. So how an electron responds to the magnetic field is possibly very different than how it responds to any electric fields that are in the system. So I'm going to now show you what those both are. Okay, so F equals Q E plus V over C cross B. This is the Lorentz force. I should write this here. This is a core thing. F equals Q E plus V over C cross B. This is the Lorentz force. So F equals QE is I've got a little charge, it's got some electric field, it gets pushed by that electric field in that direction. If it's moving and there's a magnetic field, then the V cross B term will cause it to hook around the magnetic field. So my electron's going to spiral around my magnetic field. How does it spiral around the magnetic field? Let's take this a little further. Let's say that E is 0. I have no problem saying that. Just make a big Helmholtz coil and cancel out the E, whatever. So then M dV vector dt equals QV over C cross B. Now I am free to turn my head however I like, so I'm going to line my magnetic field up with the x-axis. I can do that. That's a freedom I've got. That makes this all easier. So let's say that B equals B naught x hat. That's a vector. This is a vector, this is a vector. Then the y and z terms go away, so we can write out this curl. Let's write out this curl. This is equal to QV over C times the x component, x, y, z. This is how I do curls all the time, is I write a little circle, and I use this circle. This is the triply antisymmetric tensor. So the x component is Vy times Bz times plus minus Bz times Vy. Vy, Bz minus Bz, Vy. And then Vy is Vz Bx minus Vx Bz. And then Vz is going to be Vx Vy minus Vy Vx. Who goes away? You go away, you go away, you go away, you go away. So I'm just left with VZBX and VYBX. BX is constant here for me for now. So now I'm left with two equations. M d by dt of Vy equals QV over C, Q over C, QVZ Bx, and then M dt Vz equals, did you guys do this already in anywhere? Probably in EM. QVY over C Bx again. This one's minus. All right. Once again, this is one of our favorite tricks. I've got two equations and I only want one, so we'll differentiate one of them and stick the other one in. So I take a derivative of this one. So now this is d squared, and this is now dt Vz, and now I have dt Vz. Uh-oh, we've got to get this m over here. We'll cram this dt Vz into here, and I'm left with m dt squared Vy. Let's get rid of that m too. Equals, let's see, I got a q squared, I've got c squared, I've got an m squared, and I've got a bx squared, and then I've got a dt, oh no, Vy. That's it. I got a minus sign. That minus sign is important because otherwise it's exponential. The minus sign makes it go around in a circle. So I've got the second derivative of y is some crap times Vy. So this crap is the frequency. So the frequency that an electron will go around a magnetic field is the square root of this. And that's called the cyclotron frequency. and it is equal to QV over M, mass of the electron, times C, equals omega cyclotron. Okay, so that's a frequency. So we need to deal with things that are on time scales longer than 1 over the cyclotron frequency. So now, okay, I guess realistically, if I have some gas that's emitting in the X-ray and I integrate, it's still going to be emitting in the X-ray. But I don't have to worry about what the electrons are doing. From the dynamics of the gas point of view, we can ignore those. Dynamics. And the last thing we need to do, and this one is really probably more important than the cyclotron frequency, is the plasma frequency. And this is the frequency that that electrons respond to the electric field with. And the book goes through one derivation that I don't like anymore because I found a derivation that I like better. So I have a uniform sea of electrons. I'm going to take some of them and move them over here. So in one dimension, my electron density looks like this. Does that make sense? So I just take a slab, an infinite slab, and I just shove it in one direction. This gives me an electric field, or this gives me a charge. So let's say I've got some charge density that's E times N. The charge density here, if I move this by delta X, the charge density that's here is going to be E N delta X. That's just the charge that I stacked up. So we'll call that sigma because that's really a charge density, not an actual charge. It's a linear charge density, but that's all right. And that gives us an electric field. Curl E equals rho free, 4 pi, right? So dE dx equals rho free, or E equals rho free times delta X. So the electric field that I get is just E n delta X. So now F equals QE. I should write this one down. Oh, I have this one down here, right? So F equals QE. So M d squared of delta X dt squared, we'll just look at, I moved it by a little bit, we'll look at how that little bit changes, is going to equal QE, which is going to be E squared N delta X over epsilon naught. The derivation that I used epsilon naught. I'm going to change that on the fly, and I'm going to put this 4 pi here, because that's how it should be different. Okay, so I've got the second derivative of my displacement is equal to some number times my displacement again. Once again, we have an oscillator. So you think about this. I move a little bit of I move some electrons over here. They feel the electric field from the vacuum that they created. They move back over here. Then they have some inertia, they overshoot, then there's another charge again. So it's the same kind of oscillator that we get a lot. This gives us the plasma frequency is just the square root of that, and to write it down correctly, the m's got to go over here. The plasma frequency is 4 pi times the density times the charge squared over the mass of the electron. Really, it should be the mass of the lightest charge carrier, but you never have a sea of anything but electrons. There's always electrons. So the plasma frequency, omega p, is the electron response, and that's 4 pi n e squared over the mass of the electron. So, as long as we're longer than those and bigger than that, we can ignore the electric field.
Should there not be a square root?
It should be maybe it should be square. Yes, there should be a square root. Or the thing that's quicker to write. So as long as we're big and long, and that can be dependent on the scenario. So we'll talk about how big and how long in a second. So we'll make this a little bit bigger, but a little bit better in 1 second. I'm going to derive the MHD equations, and we'll have something that looks like a Reynolds number. We'll use that. So let's get to the MHD equations. So we now know when we can use them. So when can we get rid of the electric field is when we can, and then the book goes through a little bit more careful formal derivation of this, but not a ton. Okay. F equals QV cross B, or F equals J cross B. Is there a 4 pi there?
4 pi.
Yes. And a C. Oh no, the C's not there. The 4 pi is just there. No, I'm sorry. Derp. Squirrel brain is not on fire today. 1 over C, J cross B. Because it's just like this, and that C is there. And V times Q is J. That's pretty simple. If I have charge and I push them, that's a current. So F equals, this is just QV cross B, except we made this a J. And what else do we know? We know that curl of B is 4 pi over Cj. That's just this. Yet again, Maxwell's. So we can rewrite the force is equal to 4 pi over C del cross B cross B. Now, where those parentheses go matters. You can't move this parenthesis. It's got to be right here. If you write this as curl B cross B, you'll get something really strange. If I write it like this, then I get 0. Right? A cross A is 0. So you got to be careful a little bit with this equation. So this is the force. So we can just pack this onto Navier-Stokes equation. So Navier-Stokes says dV dt. Actually, let's write this here in my equation barn. Super didn't need to take the time to write that. So dV dt plus v dot grad v equals 1 over rho grad p plus 4 pi over rho del cross b cross b. This is force. This is force per mass. So that's why we get to pick up a rho here. A lot of times that rho goes to the other side, and I deal with the momentum equation. That's a better thing to deal with. Okay, so this is, I don't know if this equation has a name. It might, now you can also put in a lambda del squared v here, but we're always going to ignore this term for what we do for now. This is where there's no astrophysics in the first half of this course. In the second half of this course, most of this is motivated by astrophysics. So in an astrophysical setting, the viscosity is so much smaller than anything else. The Reynolds numbers are so large that we can get rid of the viscosity.
Where did C go?
Which C? Here. There's a C here and a C here. This is J over C, J over C. All I do is pick up a 4 pi. Yeah.
Yeah, I was confused there. When you plug in del cross B, why doesn't it become 1 over 4 pi?
Where?
For the
Oh, maybe I wrote it wrong because I'm. Yeah, thank you. Sorry. That was better. Right. Yeah, because that 4 pi should be there. Okay, so here is the force equation. And sorry, when I do this in code, the 4 pi goes away too. So I kind of forget where the 4 pi is supposed to be. And I screw that up from time to time. So we can write down a generalized Ohm's law. What's the Ohm's law? Ohm's law is V equals IR. Remember that, right? We'll just put the sigma over there. This is voltage, not velocity. Maybe I should make this a big V. This voltage is voltage times conductivity is the current. This is the current. Here's the conductivity. Here's my electromotive force, my EMF. Is both of those two things. So let's solve this a little. I can derive this general Ohm's law in a minute. I will do that in a second, but just trust me for now. Solve this for E. And you're left with E equals J over sigma minus V over C cross B. We also know that dB dt equals minus 1 over C del cross E. Cool, so I take this and I stick it in here, and I remember that J is curl B, and I'm left with dB dt equals del cross V cross B plus lambda, I'll show you what lambda is in a second, del squared B. This del squared comes from the fact that I take the curl of the curl, and lambda is where all my 4 pi's and stuff go. This is C squared over 4 pi sigma, where sigma is the conductivity. So this is the other important equation. This is the induction equation. We'll write this down here in white. So one of the things that we want to ask is, when can we skip this second term? Because this is an equation that looks a lot like Navier-Stokes. And we spent a lot of time talking about how much this combination of a nonlinear term and a diffusive term kind of sucks. So when can we get rid of the diffusive term? When do we have to hang on to this term? When do you use which? So it all depends on, you can define another Reynolds number, a magnetic Reynolds number. Was the same L times V over this time lambda. There's no B in here because the B is in every term. So it goes away. It cancels out of my units considerations. Here I've got an L and a V, and here I've got 2 L's and a lambda. I take the ratio of that and I'm left with LV over lambda. So this magnetic Reynolds number determines whether or not you need the diffusive term or whether or not you need the induction term. Now you really ultimately need both all the time, but a lot of the times you can ignore one or the other, just like we did with Navier-Stokes. So these are our new equations. We're not going to use Navier-Stokes much for the rest of the semester because we're going to include this magnetic term. Magnetic term is fun and fascinating. The last thing I'm going to do is show you where the resistivity comes from. This derivation is kind of hard to follow, so stop me if you get lost. So I'm going to just write something down. The book derives this a little bit more carefully. I'm just going to write it down and tell you where all the terms came from. So it's basically F equals MA. I'm going to write it the other way. I'm going to write MA equals F. So MA is equal to the mass of the electron times the number density of electrons times d by dt, the velocity of the electrons. And that equals minus grad of the electron pressure. That is the pressure that electrons bouncing off of other electrons has. So when I have electrons bouncing off electrons, that's the electron pressure. Minus N times E plus V over C cross B is the Lorentz force. This is my QE and my QV cross B. And then I'm left with ME N VI minus VE times nu C. Okay, let's annotate this thing. Okay, so this is electron versus electron. This is the Lorentz force, and this is electron versus ion. So this first term makes sense. It's just gradients of pressure. We've been dealing with that all year. The second term makes sense. It's the Lorentz force. The third term is a little trickier. How do I see a force out of that? So think about momentum exchange. When I have an electron and an ion and they bash into each other, they're going to swap momentum. The momentum is the momentum transfer is going to be equal to the mass of the electron times the number density of electrons. We always have to be working in a density because this is a continuum mechanics. Times the difference in velocities, VI minus VE. So this is the relative velocity difference between the ions and the neutrals. And this is the mass of the electron. So this is the relative momentum that an electron has relative to the ions. Now, if your temperature is really high, this might be relativistic, and then you've got other problems, but we're not going to deal with that today. Times the collision frequency. So this is the frequency that you're getting momentum from the field of ion into the field of electrons for the field of ions. So what I've done is written an equation for the velocity of electrons, really the force on electrons, which goes like a pressure Lorentz, and this exchange term. Now these two are good and useful, and we need them, but we're going to ignore them for a second and just think about what this term is telling us. Actually, so let's say I get another equation just like this for the ions. The only real difference is I replace all the E's with I's, and this swaps sign because the exchange goes the other direction. But it's the same size term. So let's talk about what this, so let's do something. Let's say we're in steady state, and it's unmagnetized. Then we're left with and let's call it uniform. That way I can throw out that gradient. Then I'm left with this equation. Just becomes 0 because it's steady state, equals 0 because it's uniform, minus n E times the electric field. That term goes away because we said it was unmagnetized. And then we're left with this last term, MEN VI minus VE times nu C. So let's just rearrange it a little bit, and we're left with, oh, we got to define something. This. The electron charge times the difference in the ion and the neutral velocity. My notes don't make sense. I have a typo. Anyway, we're going to run with it if I'm missing a term that's in the book more accurately. So E times the velocity difference is the current, because that's the net charge, the net velocity charge times the charge, or the net velocity times the charge. So I can rewrite this whole thing as E equals eta times J, where eta equals ME times the collision frequency over the number density times the electron charge squared. This is the resistivity. Now, I'm not done yet. I'm going to make this, I've got to turn this into numbers. So I wrote down this equation that describes how an electron moves around, and it's got this term at the end. This term at the end is the current, and it's going to have the actual banging together of all the stuffs. The only thing that we don't know in here, so I know the mass of the electron, and I know the number density, that's a free parameter. I know the electron charge. Well, what's the collision frequency? We got to sort that out. Let's see. Do I have another board? I don't want to erase it. So the collision frequency how do I sort out what the collision frequency is? Boop. I want to know what the let's see. Most of you took XCal. Remember doing relaxation of clusters, and there's that long, horrible two-body relaxation method, and we go through this long derivation, and then I say it's irrelevant for big clusters. The reason that I go through the derivation is because the same derivation is useful right now. So the basic idea is I want to know, I've got a sea of things. They're electrons, let's say. I'm going to take another thing and I'm going to bash it through, I'm going to shoot it through my sea of electrons, and I want to know how often do I run into more electrons. So we think about, I've got some velocity, I've got some cross-sectional area, so what's my cross-sectional area? And I've got some density of particles. So the length of this is V times delta T. And the area times V delta T times the density equals the number of things I hit. So I have a particle, it's this big, it's shooting through a sea of gas for some time duration with some velocity. It's got some size, there's some density of particles. Sigma times the length of the tube times the number density of the tube. This is just counting. I just draw an imaginary tube in my fluid and I just count all the particles in it. That's how many particles I'm going to hit. Now, I don't want a number of particles. I want a rate. Which is as easy as just getting rid of the T. So the rate of hitting particles, nu E, is equal to the cross-section of an electron times the velocity times the number density. I was using U in the notes for the velocity here. I'll continue doing that. So the only thing we need to sort out, so V is going to be the thermal velocity. The density is a free parameter, so this is a knob that I have. This is something that's going to be determined by the system. The cross-section, what's the cross-section of an electron? How big is an electron? Does anybody remember? Small. Not that small, though, because they've got an electric field. And that electric field is pretty big. That electric field fills space. So one electron, the electron itself is a point and takes up basically zero space, but its electric field is pretty large. So we need to sort out how large that is. So what we're going to do, we're going to wave our hands enough to fly. The change in momentum is equal to the force times the time scale for which that force is acting. Now I've got an electron and I've got another electron. And this electron comes here and hooks around like that. What's wrong with the way I drew that?
Wait, that's going the wrong way.
Sure is. I realized that after I drew it. Maybe I just let you guys in on the puzzle of why Squirrel Brain drew the wrong thing. It's going to go like that, right? So there's going to be some minimum distance. We're going to call this R naught. And we're going to say that R naught is really most effective. It's most useful when delta P is about P. So when I basically change by 90 degrees, that's the cross-section. If I look at bigger, I mean, there's still going to be some impact as I go further away. So there's always an effect because the electric field fills space. So we're going to say that the cross-section is determines R naught, and R naught is determined by when my electron is scattered by 90 degrees, where the change in momentum is equal to the momentum. So let's flesh that out a little bit more and get something real. Oh, how am I on time? Oh, is this over at 2:30 or 2:35?
35, for sure.
I think that's right. That means I have more than 30 seconds to finish this thought. Okay, so F, the force between two electrons, is E squared over R naught squared. And the time scale for this collision is going to be kind of like R naught over V. There's the hand waving. Now this is equal to the change in momentum. And we need that to equal m times v. Right? So now we solve this and we say that the size of my electron is equal to E squared over me times v squared. I started using v because I always do. I can't use u as a velocity. Sorry. You all right?
Yeah.
So my cross-sectional area is E squared over m times v. Now this is kind of cool. The size of an electron depends on how fast you're running at the electron.
I'll
Does that
take
make
your word for it.
I just showed you. I'll show you again. So what we're saying is I've got a thing here. I'm running at it. The size of the electron is, so I want to measure the size of the electron. I've got an electron, I got it here. And I'm going to measure the size by shooting other electrons here. And where they stop showing up, that's where the electron is. That's where the other electron is. They're going to stop showing up. But if I'm way over here, it's going to go basically straight. It's not going to start getting deviated until I get pretty close. And then they'll be deviated by a buttload, and then it won't be deviated by quite as much. Does that make sense? So what we need to solve for is when is that deviated by a buttload? What is that size, R naught? So we say that this R naught is when I get close enough that the electron deviates a lot. So that is this statement. Delta P is roughly P. So this is delta P and this is P. And that defines R naught. So R naught is defined by the time that that one electron is passing the other one, and by the amount of force that it gets to experience. So the amount of force that it gets to experience is just QQ over R squared. That's just the electron force. So this is just E squared over R naught squared, times the time scale, which is R naught times V times M. So what this is doing is saying we're kind of defining the size kind of backwards or inside. I'm saying that when delta P is equal to P, that is going to give me R naught. So I write that down with R naught, and then I solve, and then I'm left with this. But I see that there's a velocity left over because I'm talking about the sizes has to do with the V. So if I think about this experiment where I have an electron and I'm trying to measure its size by shooting electrons at it, if I shoot real slow electrons, they're going to get deviated by a lot, right? Because they have plenty of time to experience all of that force. If I shoot it really fast, it's going to go straight. It's not going to see it as much because it doesn't have as much time to be deviated by the force. Its momentum is large. Does that make sense? So how big this electron is depends on how fast you're coming at the electron, because that depends on how wide it gets. So the way we say that formally is the cross-section depends on the energy. So we have an energy-dependent cross-section, yeah.
So is the faster something you're shooting at it, the more accurate the result is? Or is there like a sweet spot where you're getting the most accurate?
Accuracy is probably most determined by how you set the experiment up. I think that you could make it accurate in any of the scenarios, but you probe more things if you hit it harder. If that helps. That's a very interesting question. I will ruminate on that and see if I come up with a better answer. Where am I? I'm not quite done yet. So this is my cross-section. This is what I care about. What I care about, the reason that I'm doing all of this, is I need the collision frequency. I need the collision frequency because it's in my resistivity. And it's in the resistivity because that's what the current does. So we need to know how fast electrons and ions bounce off each other. So we need to know how big an electron is. So we need to know, and that's going to tell us the resistivity. And in a second, I'm going to get a just awful equation that I just pull out of my bag because I'm not going through the whole derivation. I'm just doing this hand-wavy derivation. Okay, so R naught is this, and the size of an electron depends on the energy of the electron, also the energy of the thing that's looking at the electron. Let's see, I'm just going to skip to the... so this gives us that, and if we call the velocity, what's the velocity of an electron in a gas? KT over m, square root of that. So KT over m is the velocity. So if we take this velocity and we take that, and then we do something that's a little bit more complicated. So okay, we need to do all of those things. So that gives us what the cross-section is, or what the resistivity is. If you do a little bit better job, let's see. So I got that the resistivity is equal to pi times m e to the 1/2 times e squared over kt to the 3/2. Anyway. So this is kind of hand-wavy. A much more complete derivation that you can find in Spitzer's outstanding book on the interstellar medium. If you're interested in astronomy at all, like pursuing it, I would definitely pick up Spitzer's book from 1977 because it's really great. So many things you're like, that seems kind of bullshit. Spitzer probably derived it, and it's not. So there's a lot of things in this textbook on the interstellar medium. So from this textbook, he derives that the resistivity is more accurately pi to the 3/2, mass to the electron to the 1/2, the atomic number of the ion, that's missing from all of this, times e squared divided by some number gamma times v times k t to the 3 halves times log of this thing called lambda. But it's the log. What's the log of 1,000,000? 6. What's the log of 10 million? 7. 10 million is way bigger than 1,000,000, but 6 is not much bigger than 7. I love the log. The log might be my favorite math tool because it's so handy. So it doesn't matter how big this thing. This thing is like 10. And it's always going to be about 10. Maybe it's 11. Maybe you get 14 if you have a really large thing. But so lambda doesn't matter. You can look it up. You can look this up, and it's in the books. So this gives you a value of 7.3 times 10 to the minus 9 times the log of lambda over kt. T to the 3 halves. This is called the Spitzer resistivity. And we're going to need this because this shows up in our MHD equations in this lambda. So this lambda is has a 1 over sigma. Yeah.
You have a z in the numerator and denominator. Is one of those supposed to be something else?
Oh, maybe this is a 2. And there's a 2 in there. Thank you. That is a 2. That's why I write a little line on my z's most of the time.
Is it resistivity or conductivity?
The way I wrote it is the conductivity. Oh, wait. Nope, resistivity.
You said resistivity and wrote conductivity.
I know, Squirrel Brain decided that I was wrong, and it was the conductivity. So I wrote that, and then I realized I was right the first time. It is the resistivity. The only difference is 1 over this. So once you're like 4 pages into a derivation, sometimes it's easy to forget where you came from. Okay, that is what I got for today. That sets us up with plasma physics. I'm not going to do most of this again, because most of this is it's all very interesting, but we're going to just use the MHD equations. And we'll talk about that because they're fun. Man.